Hello, this is the next video in a playlist that I'm calling Combinatorial Results. And this is part 2 of a little mini series that I'm calling Probability of Sorting Cards Correctly. In part 1, we talked more about the formula and a little bit of the theory of how to calculate these probabilities. And in this video, we're going to do it using the R statistical software package. So first, let's just create a function to calculate the exact probabilities. And it's kind of a neat function. I'll tell you why in a second. But first, the variables are piles, which is the number of piles that we're sorting cards into. So for instance, if we're sorting a deck of cards into reds and blacks, then piles would equal 2. And n is the number of cards in each pile, so that'd be 26. But this is the function. I call it prob sort. And I have one error check, and that piles must be 2 or more. I don't have any error checking that piles is an integer or anything like that, so you have to be careful when you use this. But it's the code right here that I really like. And there it dynamically generates this code based upon how many piles you have and how many numbers you have. And so if you watch part 1, the probability ends up being a factorial in the numerator and then the product of several binomial coefficients or combinations, something choose something. And this dynamically generates that. And so it's kind of neat if you want to study that and look at it. And with all my R videos, I copy and paste the code into the comments so you can copy and paste it into R and run these. So here's a few examples. So probability of sorting 26, we have 2 piles, 26 cards in each pile, so it's 52 cards. And the probability of sorting them correctly is 4.03 times 10 to the minus 15th. So that's the probability of sorting the reds and blacks. If we have 4 piles, 13 cards per pile, this is the probability. And just to illustrate that you can do it. So if I say the piles is 1, you get an error. Really, I should probably say it's 100% or 1. If we have 3 piles, 13 in each pile, that's the probability. And this one here, so if we look at, we have 3 piles, 1 card in each pile, then you are going to sort them correctly every time. So this should register 1. So it does, probability of 1. Now, in the simulations that we do, so this is if you want to calculate probabilities one at a time for the situation you're interested in, that's the way to do it. Now, in the simulations, I create a function that's called all_vec equal. So I need to see if all the components of a vector are equal. And there's not a standard R function. So this is the function that does that. And so if we want to see if the vector 1, 2, 3, 4, 5 are all equal, it's false because of course it's not. Or if they're all A, if they're all 2, and then that's true. Now the simulation is, we do 2 simulations, and for different reasons. So when you're doing a simulation in a lot of languages, you do a simulation once, and then in the next iteration you do it again, and the next iteration you do it again. Well, if that's your mentality in R, simulations are incredibly slow. And so you have to vectorize them or put them in a matrix somehow. And so one approach that I really like is to just think of a row of a matrix as a sample. That's one replication. So if we create a matrix of size 200,000 by, the number of columns needed, then each row represents a replication. And then you can very quickly do calculations over that matrix or by row even. And that's a very efficient way to do simulations. So if we do this, so we have 2 piles, 10 cards in each pile, and we're doing 200,000 replications. So let's look at this. So 1, 2, 3, 4, maybe 4 or 5 seconds. And so the simulated results are 1 to the minus, times 10 to the minus 5. And the actual probability is this. And so we're close. And if we were to run that again, this would be slightly different, or, similar at least, but, and so, but one thing is, these probabilities we're calculating are so small, you have to do millions of replications to even see one event. And this approach is so inefficient. So let's say, like my crappy machine that I use, if I have a matrix of 2 million by 20, it actually shuts off. The R closes because it can't manage that amount of data. So this approach, if you want to do a few million replications, this is not the approach. And so one approach that I have done, that I do, is this. I'm gonna call it simulation B. So it's the same approach where we have so many cards in each pile. We have so many piles, and we want to find the probability. So this is actually the same: 2 piles, 10 cards per pile. But what I do is I create a matrix that's much smaller, and so I can do the calculations over a matrix with 10,000 rows or 100,000 rows pretty quickly. And then the next iteration, I just overwrite that and do the calculations, saving them as we go. But that way I don't run into memory problems. And my little machine, I can do, tens of millions, if not 100 million replications in this way by using the same smaller matrix over and over and over. So here I use a matrix of size 10, 10,000 rows by, it ends up being, 20 columns. But then I iterate this 20 times and I get the same 200,000 reps that we did in the previous simulation. So otherwise it's all the same. And let's just look at that. So 1, 2, 3, 4. Yeah, so this ended up being a little quicker, maybe, but it's not designed to be quicker. It's just designed to not run out of memory when you're doing these simulations, and that's what this approach is for. And actually, I would try to understand what I just did, because it's going to help you in your career. Now, here in the video, the first video, we looked at sorting cards into different number of piles. So let's say there's an original probability of sorting 52 cards into reds and blacks, but how many cards would I need to sort into 3 piles to make that probability roughly the same? And so this is what this does. This loops over piles, and it loops over the number of cards per pile. And so it just keeps going until it finds the right number. So this is the number of piles. We're going from 3 to however many we do. It looks like we're going to do 20. And then this while statement is the workhorse. So we keep adding cards to our deck until that probability becomes a little bit less than the probability of sorting 52 cards into reds and blacks. Then it knows that and records it, and then goes to the next iteration. And so that's what this is doing. And so let's look to, I think I need to make it bigger. So here we are. So 2 piles sorting 52 cards this is the probability. And so that's the probability of sorting into reds and blacks. But if we have 3 piles and 36 cards total, so that's 12 cards per pile, that probability is a little bit less than sorting into reds and blacks. But we have 3 piles, and then 4 piles is the same, and etc. And I'm going to plot this because I think it's interesting. So let me move this over and make it big. And so this is what we just calculated, these probabilities. Now, to me, it's kind of interesting that it hovers around 30 for a while, and then of course it goes up. But if we look at, say, 15 piles and larger, it just takes 2 cards per pile to have a smaller probability than sorting, a deck of cards into reds and blacks. And so if we take away 15 cards, then we have 1 in each pile, and of course that probability is 100%. At 14, We need 3 per pile to be a little bit less than the original, and etc. Anyway, it's a kind of a neat little plot. All right, well, that's all I have for this video. And as always, I'm going to copy and paste the code into the comments, and I'll try to pin it so it stays on top. I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.